Okay, so we are going to do problem 103. And it says a certain string can withstand a maximum tension of 40 newtons without breaking. A child ties a 0.37 kilogram stone to one end and holding the other end whirls the stone in a vertical circle of radius 0.91 meters, slowly increasing the speed until the string breaks. So we got to answer where is the stone on its path when the string breaks, and what is the speed of the stone as the string breaks. Okay, so a couple things to note here. One, you have to pay attention to some of these things when there's not a picture given. So it's saying that there is a um, vertical circle. So that means it's going more head to toe than it is going over his head. So we'll draw a circle to represent that. Then we're going to go ahead and write down the information that was given. So remember it said the tension of the string can withstand 40 newtons. And then we're given the mass of the stone. And the radius of the circle. So in order to figure out where the stone is going to break, we're going to use our equation we just learned in the lecture, the centripetal acceleration equation. And of course, this is pointing towards the center, hence the centripetal part. So we want to look at two places in order to figure this out. We're going to look at where the stone is at the top of the circle and then the bottom of the circle. So first we're going to look at the stone at the top of the circle. And we're going to do our little free body diagram here. So gravity is going to be pulling directly down. And then we're going to have tension pulling directly down. And then we will have our third vector pointing down, which is the centripetal acceleration portion. This is regular coordinate system, regular XY coordinate system. We're only dealing in the Y right now, so I'm just going to write a Y. Okay, and then like I said, here is the centripetal acceleration part that is pointing towards the center. Since we picked the top, that has to point straight down. So we're going to start with Newton's second law as we learned it, just your standard F equals ma, only we're going to set it up for the equation we're actually doing. Again, everything's in the y direction, so we're just going to deal with the y. So we're going to begin by, we have the tension just from the free body diagram. We have mg, and this is going to actually equal the acceleration portion. So you have the mass, and then we have the centripetal acceleration portion, right? So we're just going to fill that in right here. Now, if you notice all these things are negative, that's because it's pointing downward. So we're going to just go ahead and solve this. You can see that it's all negative signs, so we can get rid of the negative signs and just make them positive. But we're solving for t, so you're going to have m times the acceleration part. And then since we made them all positive, now mg is going to become negative on this side. So we'll just write that in here. And so then we have the stone at the top of the circle. This is the tension that's creating. So you have basically the centripetal acceleration, and then we're subtracting the gravitational portion. So now we need to look at the stone as it sits at the bottom of the circle. Same deal, same axes. We're going to look at the stone at the bottom. mg remains the same, right? It's always pulling it down. But this time, since it's at the bottom, the tension is now pulling still towards the center of the circle, so it's pulling up. And then again, just like before, we're going to have the acceleration portion, and that's also going to be pointing towards the center of the circle. So both the tension and the acceleration are now pointed upwards. So let's get back to the Newton's second law. Again, summation in the y. So same deal as before, we're going to write the tension. And then we're going to subtract the mg portion. And then this is going to equal the mass again times the acceleration, but because the acceleration is moving upwards this time, we can go ahead and make that positive. So when we go ahead and solve this the same way we did before, we're left with the same equation, only this time we can see that we're adding mg instead of subtracting, right? So at the bottom of the circle, the mg portion is being added, so the tension must be greater, right? So if it's going to break, it has to break at the bottom of the circle. So we figured out that the most amount of tension is going to be applied at the bottom of the circle, and that's the answer for where it's going to break. Now you're going to have to put in some numbers. The equation basically at this point has been finished. Physics is over. So now we can just plug in some numbers real quick and get a numerical answer. So just going to rearrange this because they're asking for the velocity. So we're solving for velocity. And so this is the equation that you should get when you solve for the velocity. At this point, then you want to start plugging in numbers. So we have the radius, we have the mass of the stone, we have the tension, and then we have gravity, and then mass again. So when you do this, put it in your calculator, you should get an answer of 9.458, and that's a velocity, so it's meters per second. And then, of course, we can limit this down and say it's 9.5 meters per second.